All right. It's already 3 minutes past 1. Let me start today's webinar. First of all, good morning, good afternoon, and good evening. We have some good registrations throughout the world. So based on the time, I would like to welcome you all for today's webinar organized by Geofabrics. So on behalf of Geofabrics, I would like to welcome you all, particularly focusing on designing GCCM to ASTM standards. Before I hand over the presentations to Nick, I would like to just put some ground rules. So all are muted. So if you want to ask any questions, please make sure you add that questions into your Q&A tab. You can find that one at the base of this particular screen. At the end of the presentations, Nick and I will go through and try to answer all the questions. Let me introduce you to our today's presenter, Nick Customers. Nick is actually working as a concrete canvas technical and commercial manager for Oceania and divisions. He is a qualified civil engineer, has been involved in building and civil construction for over 35 years. And over the last 25 years in technical marketing of the geosynthetic products. I'm pretty sure you may know him well because he started working for McAfee in 2002 as a sales engineer, and he actually headed various technical and sales roles since then, including 5 years of running his own geosynthetic consulting practice. Now, during this period, Nick also introduced various new products toward this region, including welded mesh, gabions, geomembranes, and bituminous membranes. He is appointed as a commercial manager for concrete canvas in 2015. And from this day, he involves working with distribution partners like Geofabrics Australasia, different specifiers, asset owners, contractors, and regulators to ensure successful delivery of the project incorporating GCCM solutions. I won't take you too much time. On behalf of Geofabrics and all the attendees, I would like to ask Nick to start his presentation. Nick, floor is yours.
Thanks very much, Rajesh. Thanks everyone for tuning in to listen about GCCMs. As Rajesh mentioned, my name is Nick Customers. I'm Technical Manager for Concrete Canvas in the Oceania region. I've got to say there's a lot of content in this webinar and I am going to go fast through it so we don't go over time. So that's the reason why I'm talking this fast. Most of my days I spend working with our partners, Geofabrics in Australia, and their clients, assisting designers, contractors to successfully deliver GCCM technology in their projects. Basically for the last 7 years that I've been here, if there's any technical problem with GCCM, the buck comes back to stop with me. So I've had a lot of experience in the last 7 years of what the problems are with GCCMs. So we'll get straight into it. This presentation will cover, there's basically 4 sections. First is an introduction to what is a GCCM. Now I'm going into 4 different approaches to help people better understand GCCMs overall. The second section will look at the basic design procedure for how to design to ASTM D8364. We look at the application, the grade, the panel layout, jointing, anchoring, all those things. Then I'll go through a couple of quick work examples and show you what a typical sample specification is for a slope protection project, channel lining and bund lining. And then we'll finish off with some quality assurance statements or notes that should be put in specifications or tenders to make sure that the product conforms with ASTM D8364. Excuse me. So first up, what is a GCCM? As I mentioned earlier, we'll look at 4 approaches. Firstly, we'll look at the descriptive definition, describing the materials. Then we'll look at an engineering analysis of how a GCCM functions. We'll look at how a GCCM should be manufactured and why it's important. And we'll look at what are the minimum performance requirements for a GCCM. That is the new standard. It's about 14 months old now, ASTM D8364. Okay, according to American Standard which has the standard terminology for geosynthetics. A GCCM is a geosynthetic cementitious composite mat, a factory assembled geosynthetic composite consisting of cementitious material contained within a layer or layers of geosynthetic materials that becomes hardened when it's hydrated. So that's that definition here. There's a couple of types. The normal GCCM has got a, in this case, PVC membrane or geotextile underneath. These normal GCCMs are used for protection and erosion applications. We can also add a geomembrane to the bottom, and we get a GCCB, which is a geosynthetic cementitious composite barrier. And these products perform the protection and containment function. Okay, now we'll look at, that's the definitions. Now we'll look at how a GCCM functions, an engineering analysis of GCCMs. So GCCMs combine the properties of geotextiles with the properties of concrete or cement to create a geosynthetic cementitious composite material, which utilizes the desirable properties of its components. And a GCCB is the same, except it also adds a geomembrane layer and therefore a containment function, as you can see here. Okay, an important point to remember is because you have a cementitious component and a textile reinforcement component, GCCMs work similar to reinforced concrete. Now, in a GCCM, the way they work like reinforced concrete is the geotextile layer provides the initial carrier function, like formwork, to hold and restrain the cement fill to the required dimensions to create the thickness of the product, and very important, the density of the cement. Tensile reinforcement also reinforces the cement fill. A note here that geotextiles degrade quickly once exposed to UV and weathering, so the top geotextile surface is deemed to be redundant once the GCCM is in service. In fact, technical papers show that geotextile is expected to lose greater than 80% of its initial tensile strength after 48 hours of UV exposure. So, sorry, I'll go back a step. The important point to remember here, for the tensile component, the geotextile, the index test for geotextiles is tensile strength. Now we go on to the cementitious component of a GCCM. The cement fill, after curing, provides compressive strength, hardness, which give the composite product its long-term durability, its hardness, and its abrasion resistance. Now, the index test for the cement component is compressive strength. Now, why that's important is you got a composite product, you got tensile strength, which its index test is tensile test. You got a cementitious component whose index test is compressive strength. But as a combined GCCM, we can evaluate the properties of the tensile reinforcement and the cement component by bending tests. That way we reveal how the components work together. We reveal the tensile strength provided by the geotextile and reinforcement, and we reveal the compressive strength provided by the hardened cement mix. So the point to remember here is for a GCCM, index test to test quality is flexural bending according to ASTM 8058. We also have some test data showing that flexural bending test, so the 24-hour initial flexural bending test according to ASTM D8058 can be correlated to 28-day compressive strength as to ASTM D8329. Okay, how a GCCM should be manufactured and why it's important. This is purely my opinion, but it's based on experience and supporting data. A GCCM should be manufactured on a custom design manufacturing line, which can ensure three things. Firstly, that the cement is placed into the geotextile under pressure. Secondly, The cement remains under pressure when production is completed. And thirdly, there are no voids introduced into the process. Why is this important? It's important because a GCCM, having a cementitious component, it's all about the concrete strength, is all about the water cement ratio inside the GCCM, known as the WC ratio, which all engineers would have come across in Concrete Technology 101. The strength of cement is based on the water cement ratio. Okay. We have here on the right, we have a concrete design mix chart, which shows the compressive strength of the concrete on the y-axis and how it can be affected by the water cement ratio on the x-axis. As I said earlier, the final water to cement ratio is the most critical parameter of any GCCM. And I'll show you why. Now, if we get 1 kilogram of 80 MPa concrete cement, and we add to that 300 grams of water, we get 300 grams over 1,000 grams, give you 0.3, gives us a water cement ratio of 0.3. So this particular dry 80 MPa concrete cement, when mixed with 300 grams of water, according to our graph, this is our water cement ratio down here, gives us a concrete strength when tested as a cube of 80 MPa. Now, if we take that same dry powder, 1 kilogram, but this time add 800 grams of water, we get a water cement ratio 0.8. So now we come down to 0.8 and we get a new compressive strength of only 24 MPa. Guys, what you've got to take away from this is it's the same 1 kilogram of dry powder. There's no additives added, there's no fillers, it hasn't been improved or anything. The only thing that's changed is the amount of water that's been in contact with the cement and mixed in, and that produces a decrease in compressive strength. Why a GCCM should be manufactured on a custom designed line is, well, 6 years ago, we looked at making GCCMs on a GCL line, which is what they used to make geosynthetic clay liners. Now, this process involves needle punching. So you've got 2 layers of geotextile on the bottom and on the top, and then thousands of needles go through this material to bind the top and bottom layer and hold the cement, or in the case of a GCL, the bentonite in the middle. Unfortunately, when we tried this process, the final process of needle punching created excessive voids in the material, which critically reduced the cement density. Okay, so going back to this graph, remember that during hydration, when you put out a GCCM and you hydrate it, the maximum amount of water in a GCCM depends entirely on the void space in the cement layer. So you can't control the water cement ratio. It's purely dependent on the amount of voids in the GCCM cement layer and then when you wet it, it's up to the void space, how much water comes in contact with the cement layer. Okay, so we've got a cured 13 millimeter thick GCCM product made on a custom GCCM line. And then we've got a cured 12 millimeter product, which was made on a GCL line. As you can see, there's a lot of void space in here. Again, during hydration, the maximum amount of water in a GCCM depends on the void space in the cement layer, which in turn affects the final compressive strength, of the cement layer. We will revisit this point later. Okay. Fourthly, what are the minimum performance requirements? So the last definition is what are the minimum performance requirements. These are set out in ASTM D8364. This is the most important definition for a GCCM for designers. And basically all the property values are set out in table 1 of this standard, which gives all the appropriate test methods and the minimum values, but we'll come back to that later. Okay. So we know what the minimum performance requirements are for a GCCM according to ASTM D8364, but I want to touch on some points as to what are the advantages of specifying a GCCM to this new standard. Firstly, designers are referencing state-of-the-art internationally recognized standards to specify a GCCM. The point to remember here for designers is designers will minimize their exposure to risk and liability by adopting internationally accepted best practice. Now, I've just pulled an extract here out of Engineers Australia Code of Ethics. It says, an engineer must act on the basis of adequate knowledge. Subsection A, practice in accordance with legal and statutory requirements and with the standards of the day accepted within the Engineers Australia community. So I can tell you now, ASTM D8364 is being adopted by more and more Australian designers. So they are accepting it as a standard. Secondly, just another note from the Civil Liability Act on the topic of negligence, the standard of care for professionals. A person practicing a profession does not incur liability in negligence arising from the provision of a professional service if it is established that the professional acted in a manner that at the time of the service was provided was widely accepted in Australia by peer professional opinion as competent professional practice. Now, subsection 2 is what I'm going to concentrate in a couple more slides on this point is, however, peer professional opinion cannot be relied on for the purposes of this section if the court considers that the opinion is irrational. And I want you to remember that word, irrational professional opinion. Okay. Other advantages of specifying to ASTM D8364 is it's a generic specification. It does not refer to any brand names. So this allows designers to create competitive specification documents which provide value for money and minimize procurement risk. Lastly, the material properties can be validated to an appropriate test method. The point to remember here for designers is designers must ensure products are verified by independent testing for compliance. The third reason why you should specify to this standard is the standard is based on newly developed test standards specific and appropriate to GCCM technology. So the standard was developed by the ASTM D35 Geosynthetics Committee, which also designed standards which we base our geotextile standards on, we base our GCL standards on, we base our geomembrane standards on. Now, this is a peer group who designs these standards for these products in the USA. The committee includes some of the world's leading experts in geosynthetics who have reviewed and voted on the publication of this standard and its test methods. And finally, the standard includes the appropriate cured and uncured properties that a proposed product must meet to be considered to perform long-term as a GCCM. So the point to come out of this is specify the type of GCCM and minimum properties according to Table 1 ASTM D8364. Now, I mentioned a couple of slides ago about rational, and this is what I want to share with you guys. I raise this point because as until the publication of this standard, I've come across many inappropriate, and to borrow the legal terminology, completely irrational specifications for GCCMs in the past 7 years. Now, this included specifications based on brand names, for example, concrete canvas. Now, this was acceptable before this standard was published, but not acceptable anymore. Based on manufacturers' data sheets, not referencing ASTM. Of course, again, the standard wasn't published, so this was acceptable before this standard was published. It's not acceptable anymore. But then it gets really irrational. I've seen specifications based on geotextile properties, on uncured properties of GCCM. So based purely on tensile strength with no consideration of the cementitious component. So that just shows the designers had no idea of how a GCCM functions. So specifications based on mass and thickness, again, these are irrational. Based on geotextile properties, tensile strength, puncture resistance of geotextiles, again, completely irrational. I've seen specifications based on standards for GCCLs, again, completely irrational. There's also some irrational compressive strength test specifications floating around, which I'll touch on later. But basically, they contain ASTM C109. This is a standard test for compressive strength of a cement cube before it goes into the manufacturing process. And if you remember those graphs before, the water cement ratio is nominated at its optimum of 0.3. So of course, you're going to get good results. Since this new standard was published, a new method for preparing or determining the water cement ratio was published. And this is ASTM D8329/C109. So this is the same cement cube test, but now the cube test must be created at a water cement ratio that takes into account the void space inside the GCCM. The appropriate water cement ratio is determined by this standard and then mixed accordingly. So the important point to remember here is when you specify the type of GCCM, sorry, that's the same note as before. Yep, specify values according to that table. So as I said on the slide earlier, we discussed how compressive strength is critical to long-term performance of a GCCM. Now I'll take a little detour and discuss this context of appropriate test methods for compressive strength of GCCMs. Okay, and I'll make it very simple. I want to ask the audience out there a simple question. If the standard ASTM C109 requires a 50 millimeter cube to be tested, so answer me, guys, how, obviously a rhetorical question, how can we test a 5 millimeter or 12 millimeter thick GCCM if this test specifically requires a 50 millimeter cube test? The answer is we can't do it. So any publication of a compressive strength of a GCCM to ASTM C109 is not a test of the actual GCCM. We can't do it. It's not thick enough. We don't meet the standard. What we can do, and what is done, is we can make an indirect evaluation of the compressive strength of the GCCM. There's three methods in circulation. One of the common methods is they publish a standard compressive strength to ASTM C109. Now, this is testing the mortar, as I said earlier, before it goes into the GCCM, and hope that it is not affected by the time it goes into the GCCM. But we know that this is wrong, and explained earlier, as the water cement ratio will be understated. Remember, ASTM C109 nominates 0.3 water cement ratio, but this differs once the cement goes into a GCCM. The appropriate method for expressing compressive strength of a GCCM is to determine the water cement ratio to the GCCM according to ASTM D8329, then use this water cement ratio to conduct a compressive strength to ASTM C109. This gets 3 ticks. This is the correct method to do it. And we can also, as we showed earlier, we can infer a compressive strength by conducting a flexural bending test on a cured GCCM and correlating it to result of the compressive strength. This is better than the first method, but it's still only 1.5 ticks. So going back to this graph again, which we touched on earlier, ASTM C109, the water cement ratio is nominated at or optimized at 0.3. ASTM D8329 is a standard for determining the realistic water cement ratio achieved after installation of the mortar inside the GCCM as manufactured. This water cement ratio is then used to mold a 50 millimeter representative cube, which is then to be tested in compression to ASTM C109. So what all this means, guys, is that when you write a specification, the correct test method for compressive strength of a GCM must be stated as ASTM D8329 for the water cement ratio, tested as a cube C109. Okay, so again, here's this picture of a cured GCCM made on a GCCM line, and another product made on a GCL line. Now, referring back to what I was saying earlier, the compressive strength of this product, according to the standard test, ASTM C109, meets 80 MPa. But this product also, because it's the mortar at 0.3 water cement ratio, also meets 80 MPa. The point to remember here is that according to ASTM C109 method, both of these products are 80 MPa. Now, what the consequence of this is, I'll show you some photos in real practice, is here's a job that was installed 2017. So these photos are taken almost 5 years after service. The product installed here is a type 1 GCCM and meets ASTM D8364. As you can see, the surface looks pretty good condition after 5 years of service. Similarly, we have a project here installed 2015. These photos were taken after roughly 4 years of service. This is out in Broome with really hard, hot UV conditions. As you can see, the top surface appears to be in pretty good condition after almost 4 years. Now, this is a product made on a GCL line. The compressive strength value, as we showed you earlier, to ASTM C109, meets 80 MPa, but it does not meet the spec of a GCM according to ASTM 8364, which is using the water cement ratio determined by ASTM 8329. What the consequence of having a product like this is, as you can see, once the geotextile has broken up after 3-4 years, actually this is just over 3 years in service, the actual cement, because it's got a high void space, you get a lot of water cement ratio, a high water cement ratio mixing with it, means you get an incredibly low cement compressive strength of the material. So it starts to break up, it starts to crack, it starts to desiccate. And you can see, again, the geotextile, while the geotextile is intact for 3 or 4 years, the product looks all right. Then you see these alligator cracks propagating over most of the exposed material. It cracks to the extent, because the cement is so low in compressive strength, that completely desiccates and reveals the bottom geotextile layer, and even patches which were put on top to try and fix the situation, even those broke up after less than 3 years in service. So what are the minimum performance requirements for ASTM D8364? This is the table, and just highlighting each type of product. So type 1, type 2, and type 3. These are the test methods, and these are minimum requirements to meet each grade. So I'll go quickly back to those photos here. Sorry, guys, just go quickly back to these photos and show all this product broken up. But it's 80 MPa according to ASTM C109. What you've got to be mindful of, guys, is that, both of these products, if you take the mortar out, mix it to 0.3 water cement ratio according to ASTM C109, they both achieve 80 MPa. But when you determine the actual water cement ratio according to the new standard ASTM D8329, then test it in compressive strength, you see that this product achieves 79 MPa, a little bit less than the optimal value, but this product with all the void spaces is around 1.4 MPa. So as you can see here from this table, it does not meet, a product made on a GCCL line that we worked with does not meet the minimum value of a type 1 GCCM according to the standard. In fact, it's well below, and that's why you have premature cracking and deterioration of these products. So that was the first section of the presentation. Now we'll get into the designing with GCCMs. Okay, the basic process has got, here's a flow chart here. We look at the type of application, whether it's slope protection, bund liner, channel works, concrete remediation. Then we go through the design specification steps, so selecting the GCCM and all the different components. And then we'll look at the material acceptance steps, so what QA is included in your specification. Excuse me, I do have a presentation, a webinar on construction steps, more for contractors or, excuse me, anyone interested in the installation. But, excuse me, we won't go through that in this webinar. So the applications we generally use GCCMs for are all these different applications. They've been used, tried and tested as a good solution. In this webinar, we'll be going through a worked example of channel lining, slope protection, and bund lining, just to get a feel of things. First step is grade selection. Now, ASTM D8364 has got a lot of written areas, description of where a type 1 GCCM applications, where they should be used. Basically, it's for applications where there's minimal requirements for abrasion and wear, where exposure to shear stress will be less than 490 pascals, and for flow velocities up to 6 meters per second. The project will not be subject to impact loads, wave action, water overtopping, or similar forces. The GCCM is installed over a dense subgrade capable of supporting them, such as concrete or rock. There are limitations on slope protection applications, limited to slopes lower than 3:1 and slope lengths less than 15 meters long. We can extend this application by using intermediate fixings. And just a note on intermediate fixings, such as metal pegs, earth percussion anchors, mechanical fixings, or as it says earlier, where the recommended slope or length is exceeded, that's where we use these intermediate fixings. So that's for type 1. Type 2 GCCMs is similar, except now we can go to shear stresses higher than 490 pascals and flow velocities greater than 6 meters per second. It can take some impact loads. It doesn't need that harder subgrade. It's suitable for medium or medium dense subgrades. And the application can also be extended and has the same requirements for securing mechanisms of intermediate fixings. And finally, type 3 GCCM includes all type 1 and type 2 applications, but where additional flexural strength of the GCCM material due to unsuitable, that is loose subgrades, are required. The same securing mechanisms are, as outlined for type 1 and type 2 GCCMs, are also required. So sorry to hit you with all that verbal from the standard, but as you can see, the standard seems a little convoluted, and the last thing I'd want to be doing as a designer is to be going through all that verbal description and try and understand how to design a GCCM. So what I've done for you in this presentation is I've given a simplified design methodology. If you follow the entire process, the design will comply with the ASTM D8364 requirements. So to do that, the first step is selection of the appropriate grade of GCCM. Now, I've adapted this table from Concrete Canvas Literature, the General User Guide, page 5. Rather than have our different grades, we have a type 1, type 2, or type 3 GCCM. So this is a first place to select the grade of GCCM that you'll be using. The next step in the process is considering the panel layout. General concepts for layout of panels is each panel must be self-supported and stable. Fixing at both ends transfers stresses through the material from one anchor trench or termination to the other. So we rely on the strength of the material, not on the joints, which are lower strength, to transfer stresses. So what this is basically saying is a GCCM should transfer any forces to the terminations and not through the joints. So for slopes and bund lining, we do vertical installations, as you can see here and here. For channel and outlet works, we generally do transverse installations where the forces are transferred from edge to edge or anchor trench to anchor trench. Now, we said we normally use transverse layout for channel lining applications. There are some applications where longitudinal installation is suggested, and that is we try to limit it to very small channels, 1 or 2 panels wide, where there is excess material for anchoring, like this, where you have an extremely consistent cross section, like this, and when there's minimal bends inside the channel. The reason why I bring this up, and a point to remember for designers, is contractors will often push for longitudinal installation as it may be much faster, but it can compromise the design. And just to give an example here, this design here is a channel. It was designed, installed longitudinally. You got 2 joints hanging up on the slopes, which is not a good place to have them. As you can see here, there's minimal material to form an anchor trench. So I would limit longitudinal installations of channel lining to channels that take 1 or 2 panels wide, and there's plenty of material. And of course, you're going to get jobs where you have both slope applications and both channel applications. You just follow those general rules of vertical installation for slopes and transverse installation for channels, and we can work out a detail for a transition point between the two. Okay, terminations. Now, the purpose of terminations is to restrain the GCCM over the service life. It's to prevent ingress of water underneath the GCCM. The design considerations for GCCMs are we must consider the forces acting on a GCCM at the terminations over the service life. We must consider the erosive forces on terminations over the service life. Typical types of terminations we use are anchor trench, which are backfilled with non-erodible material. We use mechanical fastening to solid substrates. We use other variations like the free edge termination or the reverse anchor trench. And we'll cover those. We won't cover fastening to gabions and mesh. Not enough time, sorry. Okay. As far as basic sizing of anchor trenches for slopes up to 70 degrees, the concrete canvas technical department has made this chart, thanks Lee, and it basically determines, based on the interface shear friction of a GCCM and a soil, the soil with these parameters here, granular fill, density greater than 16 kilonewtons per meter, and fire angle of 30 degrees. Based on the interface friction, what is the length of the anchor trench to be able to support the material, depending on the type of material and the lengths. Now, this is a very simplified design method. It doesn't take into account any pegs which are put into the anchor trench, and it doesn't take into consideration hydraulic loading or wind loading for this. It's purely based on frictional angle. But what you'll find is a simplified rule again. Generally, a 300 by 300 millimeter is practical and sufficient for most designs. So that's a good starting point. And we work down from this value if required. Some of the other types of anchor trench is where you have a concrete structure outlined here, and you don't want to fasten to the concrete structure, but you want to put an anchor trench next to it. We can do what's called a reverse anchor trench. Basically, we put our anchor trench in next to the concrete structure. We install the first panel of GCCM upside down along here. We peg it, we backfill it, and we flip the material over, and we get a nice transition from the concrete structure to the GCCM without having to fasten directly to the concrete structure. All right, here's an example of it here. It's not so clear, but here we have a slip form curb and gutter. For Ballina in New South Wales, they didn't want to put any fasteners through the slip form, so we did a reverse anchor trench. Here's the anchor trench here. It's been pegged in the floor. The concrete canvas, this is the underside of the concrete canvas material. This is the top side of it. So as you can see here, the GCCM has been flipped over. That'll be backfilled to the right level with the invert of the slip form curb and gutter. Then the material is flipped back over. So we get a nice transition from this curb and gutter down to the swale drain. When it comes to hard substrates, we can use masonry mechanical fastening It can be done with or without a termination bar. Here's an example without a termination bar. Here's an example with a termination bar. Some of the key components are similar though. Firstly, adhesive sealant or gasket under the GCCM. Secondly, the fixings must be rated according to any loads on there, and we generally do those at 300mm centers, and adhesive sealant or grout fillet to the edge as required here. Sometimes we have applications where you can't get an anchor trench here in the edge, but you want to prevent water traveling in underneath the GCCM. In these applications, we use a free edge termination, which is basically the GCCM is folded over to create a thickening. We have geotextile supplied underneath there. It's pegged at 300mm centers along there to give it the mechanical strength. And then this fillet, artificially created fillet, is backfilled with either grout or bituminous mastic. In this case, they use grout. So what that's saying is there are different ways we can create anchor trenches depending on the project. Jointing, our jointing method, the predominant jointing method that we use in Oceania, according to the concrete canvas standard overlap for warmer climates, is the screwed and sealed joint. It consists of 100mm overlap, and we pre-hydrate the underlap. We apply a single bead of adhesive sealant, 30mm from the edge, and then we put stainless steel screws at 100mm centers, as you've got here, for typical applications, and they're installed 30mm from the edge. For bund applications, we can get a lot of swirling on the inside of the bund, so our technical department has advised to shorten that spacing to 50mm screws on the inside of bunds. Intermediate restraints. Now, what happens is, in these typical applications, we use intermediate restraints along the slopes and the different sections for different applications. In slope applications, we use it to profile irregular surfaces. We use intermediate fixings to reduce joint spans to limit shrinkage. We use it at internal corners to prevent shrinkage uplift. And as you remember those notes earlier, I explained to comply with ASTM D8364 requirements of slopes. In bund lining applications, it's also used, pegs are also used to reduce joint spans and limit shrinkage, to prevent corners uplift at internal corners, and to prevent shrinkage uplift, to prevent wind uplift from negative suction pressures on bunds, and to comply with ASTM D8364. And finally, in hydraulic applications, pegs and intermediate restraints are used in the design at internal corners to reduce shrinkage. That's the batter-toe transition, for example here, because this is going to want to lift up. To distribute shear stresses for high velocity flows, which we'll touch on in the worked example, and to comply with ASTM D8364. Now, this concept of shrinkage across the panel, along slopes and along bunds, I'll give you an example of what we found. Here's a job that shrunk roughly 30mm from the top to the bottom, where there were no intermediate restraints. As you can see, this is back in 2016. This is really early days, before we understood how much shrinkage there was in these hotter climates. So what we found in this case was the top end was restrained, the bottom end was restrained, and it was basically the maximum shrinkage was in the middle. Call it, for example, around 30mm for this example. So what we found later was, when we redid some similar batters, but this time put an intermediate restraint, it broke up the spans over which the shrinkage would occur. And what we found, that while these shrinkages were large and outside the tolerable limit, which was about 30-35mm, by introducing intermediate restraints, the maximum shrinkage at these points is reduced by a significant factor, and they were reduced to amounts of around 10mm, which was within the acceptable range of the jointing systems. So this is how we detail to reduce shrinkage in joints. Okay, I think this is the last point on intermediate restraints. There's different types of sections that we must consider. Now, GCCMs, being cementitious, they shrink. So intermediate pegs are used to minimize shrinkage, as we showed you earlier, and also to prevent uplift at any change of angle in the cross section. So I've just got highlighted here on this schematic, 8 typical situations are shown. The corners with green dot are classified as external corners. So these are external corners, and they don't need intermediate restraints or pegs. Points numbered 1 to 4, 1, 2, 3, 4 are internal corners, and they need pegs to restrain them from lifting if they shrink. So the important point to remember here is if the material was to shrink, would it cause it to lift? Then this is an internal corner and needs a peg. So for example, just say point 2 is restrained here and is restrained here. If the material was to shrink, as cementitious products do, the corner number 2 would have a tendency to want to lift up and out. So we classify that as an internal corner, and it must be restrained by pegs or appropriate soil anchors. Now, the generic type of pegs we use are supplied by Geofabrics. We have 2 types of pegs here. They both have a 50mm head. They both have a recess underneath, a rebate, to take adhesive sealant to avoid to reduce seepage through the installation, and also weeds coming up through it. We have 2 lengths, 250mm and 380mm, and these have different diameters. This has a 12mm diameter, and this has a 16mm shank diameter. Now I have interpolated some rough pull-out figures of these different pegs based on a publication by the IFAI. And basically what it's saying is these pegs, depending on the density and number of blows from a cone drop penetrometer test, will give you a rough pull out for these different types of pegs in kilonewtons. So what happens if peg capacities are insufficient to resist loads? So those pegs were insufficient to resist the wind uplift on this particular project. This was a job in WA. It was above a rail tunnel. It was a high wind area. Soil anchors were used because the pegs were insufficient, because the capacities they needed were higher than those in that table I showed previously. So soil anchors were used to provide sufficient capacity to resist wind uplift here and to restrain internal corners from shrinkage. So it's a dual purpose. Point to remember here is that a better design would have been to have the soil anchors through the joints themselves, as the material is double thickness here, and we have to be mindful of the puncture capacity of a GCCM. So if the wind uplift is too high, the plate may need to be a lot bigger to resist the puncture resistance of the GCCM. Okay, finally, the note on hydration. Hydration, the final stage of installation, is hydration. The concept is to saturate all material that has been exposed on that day with more than enough water to complete the hardening process. Again, a good GCCM will limit the amount of water that can mix with the cement. The minimum amount of water reduced is half the mass of the GCCM. This is very difficult to achieve in practice. Some areas will get a lot more and others will get a lot less. As far as scheduling hydration for the installation process for warmer climates, basically we have 3 stages for installation. First stage is deployment from 7 AM to 12 PM. The contractors will lay out the panels and peg them and terminate them in place, and they'll go to lunch. Stage 2, they'll come along and do the joints. So they'll complete all the jointing and screwing. Stage 2, they will begin to 2A, I call it, because anytime this is completed, they can then follow on and start installing the intermediate pegs. This generally happens between 3 and 4 PM. And the last stage, which is the hydration phase, occurs between 4 PM to 5 PM, and complete hydration of all installed GCCMs is done. And this, the best way to specify this is 3 passes, good soaks at 20 to 30-minute intervals. Okay, a couple of points. You can't overhydrate a GCCM. The initial set is at 60 to 90 minutes after hydration. You should not touch the GCCM after this until the next day. Check the next day if the product needs rehydration. And if it still is not set, contact technical representative. Last point here, geotextile underlay. I always include geotextile underlay in my specifications. Whether the designer wants to take it on or not is up to them. I strongly suggest they do. I specify generally greater than 250 gram, 300 gram non-woven geotextile. It is not used to protect a GCCM. A GCCM does not need protection unless it is a GCCB that has a barrier underneath, in which case it's a protection layer for the barrier. The three reasons why geotextile is an excellent idea to include is, firstly, the geotextile provides a clean surface free from dust for proper installation of the GCCM and adhesive sealant. The most important reason is that if for some reason, and I call it the cheap insurance method, purpose, if for some reason over the long service life of the installation, the GCCM is breached, the geotextile confines the soil particles and prevents them eroding underneath the GCCM. I call this protection from unexpected leakage paths over the life of the installation. And finally, geotextile is well known for its plain drainage function. Placing a geotextile on a slope under a GCCM will provide a drainage blanket to wick water from the surface. Then it can be collected and diverted as required. The point to take out of this for designers is strip drains are ineffective behind GCCMs, especially on slopes, whereas geotextile drainage blankets are extremely effective. This is the most common question I get from geotechnical engineers designing slopes, but this is a topic for another day, but I'm sure it will come up in the questions. Okay, and here's an example of what can happen if you've got no geotextile under a GCCM. This is a channel lining application. Right up, further up here, what happened, there was a breach, there was a problem with the one of the jointing systems. I think someone accidentally punched a hole through it with the machine. That night it rained, and as you can see, all the fines were washed out underneath. If there was geotextile under there, it wouldn't have washed out. Okay, finally, we get into some of the design examples. So a slope protection example. These are basically the same steps that we go through in all GCCM designs. So appropriate grade, panel layout, terminations, jointing, intermediate fixings, hydration, and writing specification. And these are some specific considerations for slope protection. So the crest termination, toe termination, hydrostatic pressures, if they're there, intermediate pegs, geotextile underlay, and joints. So in this particular example, the first step was to select the grade. We go to this table, and slope protection, typically use a type 1 GCCM. As far as determining the panel layout, as we said earlier, we prefer vertical panel layouts. So we've done that here on this job. Terminations, up the top, they used a 300 by 300 millimeter anchor trench installed by a trencher at the crest, and at the toe, which was a concrete apron here, pre-existing, they put concrete anchor, pre-drilled concrete anchors with 30 millimeter diameter washers at 500 millimeter centers as the toe termination. Jointing, this is the first stage. This is the pre-hydration of the underlap. A standard overlap joint, as explained earlier, was used. And here they are after the pre-hydration process. They come along, install the adhesive sealant, and then they come along and install the screws. We install the intermediate fixings along the slopes, and then the job is being hydrated. So a typical sample specification for a slope protection job like this would be type 1 GCCM, panels laid vertically, 300 by 300 millimeter anchor trench at the crest, 500 mil centers, concrete fasteners at the toe. The vertical edges were treated with free edge termination, which I discussed earlier. The joints were the standard overlap joints, screws at 100 mil centers, and intermediate spans on slopes were used to keep maximum span less than 3 meters to prevent shrinkage. And the hydration specification was 3 good soaks at 20 to 30 minute intervals. Channel lining application. So channel lining, as far as selection of the appropriate grade, we go back to our table here, adapted table. We use a type 2 GCCM unless there's other factors. Here's a cross section that I put together for a job that we looked at. It was a 100 mil long channel, trapezoidal shape, 1-to-1 batters, 1 meter wide invert. This is not drawn to scale. The depth of flow was 300 millimeters. The freeboard up and over that maximum depth of flow was 200 millimeters. The Manning's end we used was from testing data that Concrete Canvas had done over in Austin, Texas. And the slope of the invert for this project was 10%. I get all this data and I like to check the hydraulic situation, I guess, of the project to see what we're up against. So the outputs using the US Federal Highway Authority hydraulic toolbox software version 5.11, we've got a maximum flow velocity of 13.2 meters per second and a maximum stress of 490 newtons. So that's these figures here. The value was determined according to the depth of flow. I put in, as I mentioned earlier, a really conservative figure. So I've put in 300 millimeters depth of flow plus the freeboard. So assuming there's a worst case scenario where the channel overtops and we get a flow depth of 500 millimeters. Okay, from that, we get these figures here. Now, if we have a single panel here, now I know this is incorrect and conservative because shear stress is distributed from 0 down to maximum through the depth of the flow. However, to take a more conservative approach, I assume that this whole maximum shear stress is applied across all the material that exposed to water. What that basically means, we have a panel width now, which is 1 meter wide, because in this case, we're using a 1 meter wide GCCM. It was a CC8 by Concrete Canvas. And we have 0.71 meters here, 1 meter across the base, and 0.71 meter here. So the length of the panel is 0.7 plus 0.7 plus 1, which is around, I think, 2.42. So this shear stress from the flowing water is applied over the entirety of this panel, which means we have a 1.2 kilonewton force across this whole panel. Now, the tensile strength to first crack of this particular material, CC8, which is a type 2, according to ASTM D8364, was 3.6 kilonewtons to the first micro crack appearing in that material. So there's basically a factor of safety of 3 between the shear stress and the first micro crack in this material. But ASTM D8364 says that we must pin these internal corners here from uplift. So in this case, you can see now this panel is actually broken up. So we have a 0.71 meter panel, another 0.71 meter panel, and we have a 1 meter panel. Now, when you apply that same shear stress over these segments, we have a maximum of 0.35 kilonewtons on these green panels on the sides and a maximum shear stress of 0.49 kilonewtons acting on the invert. So this is an example of how pegging and intermediate pegs and restraints are used to break up the panel length that's exposed to the shear stresses when velocities and shear stresses get much higher. So just go back for a second. So here, a single panel, the shear stress was 1.2 kilonewtons. And on this panel, when it's broken up, you have 0.35 on the batter and 0.49 on the invert. Finally, when we included these pegs, intermediate restraints, we can put them inside the joints as they are stabilizing the panel underneath, and that's segmented and shingled all the way up the channel. So this was a channel here. This is a typical specification. I'm running out of time, so I won't go through it, but basically type 2 GCCM laid across the channel, anchor trench details, joint details, intermediate pegs to resist the shear. And this is the final channel here. You can't even see the pegs inside the channel. Final application we'll look at is bund lining. Typical bund lining, we look at these 7 items, but we also look at specific considerations specific to bund lining. So again, we go to stage 1, we select our bund lining. We use a type 1 GCCM for this, for bund lining. Determining the layout, we use vertical layout. Terminations, this is a 400 by 400 anchor trench that we used at each toe of the batter. The standard joint we used was the standard 100mm overlap, but this time screws at 50mm as per the guide. You can see here in the jointing, he's applying the adhesive sealant, and now he's applying the screws at 50mm centers. Intermediate fixings to resist wind uplift. Now, we'll take a little bit of time to get into this, not too much longer though. Wind uplift is determined by the structural engineer on the job. Basically, they go to the Australian New Zealand Wind Loading Code 1170, and based on their design criteria and on the location, geographical location of the structure, they can determine for a one in 100 year design speed, wind velocity, they use 41 meters per second. Then based on all different factors and the angle of the wind and the geometrical factors of this bund, the structural engineer will determine a maximum uplift pressure on the uplift side of the bund. How this works out into calculations is, so this is determined by a structural engineer on the job as 0.54 pascals of uplift on this side of the bund. We put intermediate pegs at 4 meter spans. It was an 8 meter long bund. Basically, the uplift on each 4 meter panel is 4 meters for the length, 1 meter for the width, times 0.54 for the uplift pressure. We get 216 kilonewtons of uplift to be resisted by the joints, and the 16mm capacity peg, which we used, has a 2.9 kilonewton capacity. So we exceeded that uplift force. And again, this is a basic specification that we used for the bund. The last thing I'll touch on before I finish off is QA and specifications, and that is the GCCM. So in your design specification, you select the type of GCCM, type 1, type 2, or type 3, and the GCCM must meet all minimum requirements according to that standard. In the tendering notes, I suggest you include GCCM supplied to submit typical material QA to ASTM D8364. So they must produce material QA before they, with their tender for supply. The GCCM supplier is to submit third-party independent testing with their tender for supply. The supplier is to allow for, in his tender, 1 square meter of uncured GCCM to be delivered to nominated testing laboratory for QA testing before material is accepted as conforming. So that's in the tendering notes. Then material acceptance. So when the material is ordered, at least 1 week before material is dispatched, the GCCM supplier must deliver that 1 square meter of proposed material to a nominated laboratory to conduct 24-hour flexural bending test to ASTM D8058. If all material values are met, then the material can be accepted for delivery by the project engineer. I'll just run down because we're out of time. It must be an uncured sample. If there's further issues with the material, then the engineer can ask the material, an uncured sample, to be recut and sent out for retesting. So just so you get an understanding of this test, the 24-hour flexural bending test has a turnaround time of around 3 to 5 days. That's why I've got 1 week prior notification. Excuse me, it costs around $600. In Australia, we nominate Exelplast in Victoria. They're completely impartial from us, but we know they have the ability to conduct the testing. As far as the testing procedure, it is critical that the material be delivered in the uncured state, because the GCCM will be hydrated by the nominated method, which is complete immersion. And then from the time it's originally immersed, then we count down the time, and the sample will then be tested 24 hours after it was initially immersed. Finally, this is a flexural bending test that we do for index testing for compliance of materials. It's got 3 parts. All of them are reported in the one test. And that's it for me. Thanks for your time and any questions, guys.
Thanks, Nick. Thanks for a very nice and very informative presentation. Interestingly, Nick, I think so you answered all the question in your presentation. Looks like it. There's no Q&A, no questions actually came through Q&A today. We still have some time, so all the attendees, I highly suggest or recommend you, if you have any questions, please go through your Q&A tab, and Nick is here to provide the further assistance and information if you have any questions regarding quality control, regarding the design specifications, or any other, or installation options or problems. All right, I find first question, will the presentation slide be available? I should say this, that this presentation is recorded and will be available on our website within 24 hours. So you can have the actually recording access straight away.